Hi, kids. I'm going to talk to you a little bit about the Compton effect and the de Broglie wavelength. As you know, our first two units we talked about. Hey, look, light is a wave, and all our reasons why light was a wave was because it reflects, it refracts, it diffracts. You can have interference, all this other stuff. And then all of a sudden in this unit, it's like, hey, surprise! Light's actually a particle too! So what is it really? Well, light's a wave particle. Um, Compton, he was the one that figured out, well, geez, if light's a particle, then it should have momentum. And, like if things have momentum, they can collide. And so maybe I can have a collision with a particle in light, and surprisingly, it actually worked. There was a collision. So let's have a little bit of background here. So first, you guys need to know that this sort of famous equation, E equals mc squared, kind of a famous physics guy that came up with this. What this equation is just saying is mass is another form of energy. Okay, but anyway, so that equation, and we knew that from what we've been talking about in this unit that energy is related to h times f. It's related to the frequency. F is, I have my equation, c equals f times lambda. V equals speed. Well, you can't even see that. Sorry about that. Okay, you have the equation c equals f times lambda. So you have that equation. Well, if I plug this in, I get this. Hopefully that makes sense to you. Do some intense algebra and make one of the c's go away. I have m times c, mass times velocity. Mass times velocity is momentum. Okay. Yes, my friend Mo did say some stuff, and everything he said, he meant them. But anyway, mass times velocity. So this is really a little p for momentum. Is going to equal h over my wavelength. Now, let's think a little bit about this equation, make sure it makes sense, because it should make sense. Here's what the equation is saying, okay? That the momentum of a photon is going to be equal to Planck's constant, that really small number, divided by the wavelength of the photon. Now, if my wavelength is smaller, that means I have more momentum. That makes sense. That jives with what we said up here. Smaller wavelength, bigger frequency, more energy, more momentum. Makes sense. So then what he actually did was he shot a photon okay, at an electron, and surprisingly, there was a collision. Okay, so like if this was my before picture, afterwards, maybe my electron is going this way, and my photon is going to be going this way. Okay, but the momentum before equals momentum after. But you'll notice, because now the momentum before is just the photon, now the momentum after is the electron plus the photon. Well, that means the photon has less momentum. If the photon has less momentum, okay, this is smaller. That means this has to be bigger. Okay, and again, hopefully that all makes sense to you. But yeah, that's it. It really is. That's how it works. But the more energy, the more momentum that gets transferred to the electron, the longer the wavelength is going to be, because the smaller momentum this is going to have for the afterwards. Okay, hopefully that makes sense. That's Compton, and then de Broglie came along and said, "Hey, well, wait a second here. Well, if this is true, I'm going to do some this, and look, h over momentum. Hey!" And we call this the de Broglie wavelength. So, maybe next time you should do some algebra, and then you'll get something named after you too. But that's what de Broglie did. And what he did was actually a little more than that, because he was the one that said, well, wait a second, okay? If light behaves like a particle, meaning it has momentum, well then particles should behave like light, meaning they have, well, really when I say light behaves like a particle, so a particle should now have a wavelength and behave like a wave. Well, if it behaves like a wave, then you should have interference and diffraction and all that other cool stuff. And again, lo and behold, it's true. It does. But here's the key to this. Most macroscopic things like you and me, a baseball, the wavelength here, you're going to have h over momentum, okay? Whatever this momentum is, I don't know if I'm just kind of walking along, my mass is, 70 or 80 kilograms, and then if I'm walking at 1 meter per second, I would have 70 kilogram meter per second. Well, if I go 6.63 times 10 to the minus 34 divided by 70, I get just a ridiculously small answer. So my wavelength is crazy teeny tiny, okay? Times 10 to the minus 34th meters, okay? Just so you have an idea, okay, that, even the teeniest, tiniest parts of an atom are like in times 10 to the minus 12th meters. So yeah, I am never ever going to behave like a wave. I couldn't fit through a teeny tiny slit like this and all of a sudden diffract. Because, yeah, I'm kind of big and I could never fit through a slit that is times 10 to the minus 12th meters. So, when we're doing this for macroscopic things, you know what? The wavelength is so incredibly small that macroscopic thing it's not going to have any wave, behavior at all because its wavelength is so small. But if you have electrons, and this is how an electron electron microscope works, if you have an electron and you get those electrons moving, so you give them some momentum, the electron's wavelength, it's going to be really small, but electrons are really small. So you can actually have those electrons go through things and make interference patterns and other crazy cool stuff. But, so, de Broglie, Compton, bye kids.